And then I think I need to make sure. So I think this is large enough. You can see the board, everything is set up nicely. So then I'm just starting again and probably getting good at this now. So the topic is generating functions. And basically what we are looking at today, I open the chats in case somebody wants to say something. In the corner. So basically what you can think of generating functions are a device to relate functions with, so I'm relating a function, let's call this g of x, and I'm relating this to a sequence of numbers. A1, A2, A1, A2, A3, and that might be a finite or infinite sequence. So how could I possibly relate functions with sequences? So we have seen something before, which is hopefully, I guess, if I define a function as a Taylor series or a Maclaurin series, I think. So I'm summing over k to 0 to infinity sequence ak x to the power k. Well, on the right hand side, I have a sum where I'm multiplying the powers of x with the ak summing up from 0 to infinity, and that defines my function x. For example, polynomials I can encode in this way. So if I have a polynomial x squared minus 2x plus 1, I could also write this as a sequence. A0 is equal to minus 1, A1 is equal to, sorry, plus 1, minus 2, A3 is equal to 1, and then I can write x minus 2x plus 1 is the same as a2 times x2 plus a1. The minus is in the a1 times x plus a0 times x0, or is this still on board? Yes, perfect. In other words, I'm summing k from 0 to a k of x. So this one is my function g of x, and I have encoded the function in terms of a sequence of 3 numbers. So if you tell me the 3 numbers, I get the function back, and if you tell me the function, I'm getting the 3 numbers. And I can also do this for infinite series. And I can still get the sequence from the functions. So for example, if you plug in 0 into this function, then you get the sum over 0 to the power k, ak 0 to the power k, and what is 0 times to the power 1 is 0. 0 power 2 is also 0, but 0 to the power 0 is set usually to 1. And that means that this is equal to a0. So I'm getting an information about the sequence from the function by plugging in the right value. So, and then you can play a game of secret messages. So you want to encode a sequence of numbers. You write down the Taylor series with the ak, the sequence of numbers, as coefficients. You solve the Taylor series, that gives you the function, and then you tell your friends only that function, and if they want to have the sequence back, they have to decode it by taking derivatives or evaluating that function. So this is a bit the general idea of the game. So let me just delete everything and just write down the important stuff. So you start with a sequence ak, k runs from 0 to infinity, and you define a corresponding generating function as the sum from 0 to infinity of your Taylor X function. So the case element of the sequence A times x to the power A. Okay. So we know some examples. So for example, let's start with the sequence. A0 is 1, A1 is 1, A2 is 1. That's just a sequence of ones. Which function does the sequence of ones give me? Well, I have to write x is equal to x to the k. Okay, all my a's are 1, so I can just drop them 0 to infinity. And if you look up your reference on the formula, so maybe calculus 1, you can find the limit actually. Then you find that this is equal to 1 minus x, 1 over 1 minus x. So if I tell you g of x is equal to 1 over 1 minus x, then you tell me, yeah, your secret message is 1, 1, 1, 1, 1, 1, 1, etc. And then there's some manipulations you can do on the function side and some manipulations you can do on the sequence side. So take again the example here, x2 minus 2x plus 1, corresponding to the sequence. Let's start with the 1, A0, minus 2, A1, and 1, it's A2. So if I define a new function, h of x as g of x times x. What is g of x times x? Well, x squared minus 2x plus 1 times x. That's the same as x to the power 3 minus 2x squared plus 1x, and then maybe plus 0 to have the power 0 still in there. So I have a new sequence. Coefficient 0 of x0. So 0 times x0 if you want. 1 minus 2, 1. So what happens? I multiply the function by x. That means that all my numbers move one step to the right. I put a 0 in the beginning. So some things you can do. You can do some changes to the sequences by changing the corresponding numbers. There's a nice exercise to that, which we have looked before. So next example. I shouldn't have removed this, but no problem to write it again. Can do different things. I can take 2x minus plus 2. Let's say that for a change, that's now my sequence 2 minus 2, 1, the 1 in front of the x squared here. I could look at the function g of x times c for a constant c. C is larger than 0. Well, that gives me the sequence g of x times c is equal to 1 times c times x squared minus c, if you want 2 times c times x plus 2 times c times x0. So my new sequence is 2c minus 2c and 1c. 2c minus 2c and 1c. So multiplying with the constants changes my secret message by multiplying all the elements of the sequence. And multiplying by x changes my message by shifting everything. Okay. From this little game, we see immediately that we can also encode a different sequence. So if you have if we have a constant here in front, so maybe we're multiplying everything by c, then if our function is c times x to the power k, well, then this is just a c here. And I want to give you one more, the more general form. So if you use the general formula that the function x given by c times x to the power k times a, summing from k is 0 to infinity, that is equal to a divided by 1 minus cx. So the a is the number in front of you, and the c is the number which is within the brackets. We take the c to the power k. So if you take this formula, then this gives you a way to encode certain sequences, and the sequences look exactly like ak is equal to a times the number c to the power k. Plugging in some values, so for example, if my sequence is ak equal to 3 times 5 to the power k, so a0 is 3, a1 is equal to 3 times 5, or 50, and a2 is equal to 3 times 5 times 5, or 75. And then my g of x is as said. You take the 3, the constant, in front of it, and that's 1 minus 5 times x. Okay, so we have a way of going between representations of sequences as functions or as a bunch of numbers. So let's make a note of what we have. A sequence ak equal to c times an a constant a times, maybe you should call this constant b so you don't mix it up with the a from the sequence, or constant b times c to the k. And that means that a0 is b, a1 is b times c, a2 is b times c squared. And then your corresponding generating function, g of x, will be, so the function which you get by multiplying the ak with the k's power of x and summing everything up, that will be b divided by 1 minus cx. So that's my first example, is of this form. And then it's maybe nice to have 2 more examples, but we are not going to do much more than that. So the next one I wanted to write down is you start from ak is equal to n choose k. Maybe you should remember that n choose n is equal to 1, and n choose n plus 1 is equal to 0, and then it goes on, n choose n plus is also equal to 0. How many ways are there to take n objects out of a pot with n objects? You have to take all of them. How many ways are there to get 5 pieces of chocolate? If you only have 4, there is no way to get that. And then maybe you recall that the following formula holds: a plus b to the power n is equal to, well, you have to multiply everything out. So you're basically applying the following rule. I'm just doing it for 2. So you have to multiply a plus b times a plus b. That's the same as a times a, b times a times b, and b times b. So everything times everything. And you can summarize this as a squared plus 2ab plus b squared. So you know that, but you can also write this as a sum over here n is 2 to choose k, from k going to 0 to 2, times a to the k times b to the n minus k. That's the binomial formula. So let's write it here in the general form with n is k. So now it's not 2, but n, but it's exactly the same, a to the k. So here it's still the n is a 2. A to the k, b to the n minus k. And you're summing from 0 to n, or if you agree that all of these numbers are 0, if k is larger than n, then you can also put an infinity here. So this sequence is encoded by the function g of x equal to. Now, if we want to have here n over k times x to the k, we have to plug in x plus 1 to the power n, because then my a becomes an x and my b becomes a 1, and g of x, which is this sequence, is n over k, x to the k, then there is a 1 here. Is the sound back now? Yeah, okay, good, perfect. So I have a second sequence here. Let's remove all this. And say that you can encode ak as n over k, or if you want to do this more slowly, then it's a0 is n over 0, a1 is n over 1, etc. Goes up to an being n over n, and then an plus 1 being 0. Going on again. Is this still on board? Yes. So this is my second example. 1, 2, and they're also in the script on Canvas. And I need a third example, and I'm just writing it down. So if my AKs happen to be n plus k, choose k, so I'm taking k elements out of n plus k elements, then g of x is equal to the sum over n plus k over k, we are interested in, times x to the k, so k is 0 to 1, to infinity, and that turns out to be 1 over 1 minus x to the power k plus 1. So, wait a second, I think I made a... Yeah, so there's also a mistake in the script, and I just copied it. I want to consider this as a sequence where the n changes. And the k is fixed. So n changes, the k is fixed, So my first element is A, where I'm plugging in n equal to 0. Then I'm getting 0 plus k over 0 plus k over k. My second element will be A1, which is 1 plus k over k, etc. And then this has, the k is fixed, but if you would choose any number here, then you get 1 minus x to the power k plus 1. Okay, so now we have 3 ways of encoding sequences in terms of functions and going back. So let's do one example how it's for what it is good for. So let's look at the problem that you have a variables y1, y2, y3. And you're interested in how many ways can you write, let's say y1, y2, y3. These are integers, so they are element the set starting from 0, 1, 2, etc. So they are just natural numbers, sometimes written as blackboard n, which is 0, to indicate that I'm starting at 0. And I want to know how many ways are there, for example, such that I can choose these numbers in order for the following equation to hold. Nice. Let's make it a 7 for a start. So how many ways are there to choose y1, y2, and y3 out of the natural numbers to get a 7? So one choice is taking a 0, a 0, and a 7. Well, that gives me 7. I can also make some of these larger, so, and then I have to make this one smaller. It gives me also 7. I can take 7 plus 0 plus 0. That's also 7. You do all of these, and then you wonder how many are there. So actually, how many are there? There's a nice trick to answer that. It's kind of illuminating. Well, you have to choose. You think of a number of boards. You choose a number of boards for the y, a number of boards for the y2, and a number of boards for the y3, and that should be in total 7 boards. 1, 2, 3, 4, 5, 7. So you have 7 boards, but you're free to move these boards a bit. So you could move them, this one from there to there. And so what you're actually interested in is you have these gaps. You could write them. Can you see that these are, maybe it's more clear if I'm drawing it like this. So now I have three containers, so I need 2 separators. I have 3 containers. That gives me 2 separators. That means that I have to ask how many ways are there to put, putting two holes into a set of two holes into a set of, let me think, 7, so that's the number of boards. 2 is the number of separators, so number of boards plus number of separator slots. And how many ways are there to mark two boards out of 7 plus 9? That's 9 over 2. That's kind of a nice side observation. So, but you can also compute these things with generating functions. So let's continue with it. So, which one is the next? This one. Okay. So this is the exercise with the long text in page number 2 of the short script. So there's a little story where you have n apples. And you distribute it to 3 people, which for a strange reason are named Alice. That sounds familiar to, but the second one is not Bob like you would have in informatics, but John. And the third person is Ada. No, who is it? Aya. So, okay. So basically, you have something like y1. And that's apples for Alice. Y2, apples for John. And Y3, apples for Aya. And then y1 plus y2 plus y3. You're asking them to add up to n. And for a given n, you could do the trick I did before to find the number of combinations. But I want to show you the same thing with generating functions. So this was the topic. And there's actually something nice because generating functions allow us to work in constraints. So we want to solve this equation, but actually there are some constraints. So the first constraint is that Alice doesn't want so many apples. Alice would like to have, writing as a formula, that says she wants at most 2 apples. So that excludes having more than 2 apples. So no 3, no 4, etc. Then John says, let me see the next one. John wants at least 1 apple. And not more than 3. And finally, Aya wants 1 or 3 apples. Could write it like this. And now you're not anymore looking for arbitrary, but you're looking for integers in between constraints. So in this case, y is an element. It might be 0, it might be 1, 2, nothing else. And here it might be element, at least one apple, on at most 3. Yeah, you can take this game. Element of the set which contains either 2 or 1 apple. So, and it's kind of nice to solve this with generating functions. So let's summarize. Just Alice eats y1 apples, John eats y2 apples, Aya eats y3 apples, and these are elements of 0, 1, 2, element of 1, 2, 3, and this is element of 1 or 2. I'm just repeating in small print what I've said here. So let's write down a generating function for that. And I'm explaining why we are doing this at the moment, but let's write down first the full set. So I'm writing down f of x is equal to, and now I'm encoding my message that y might be 0, 1, or 2 in form of different powers of x. So I say x to the 0 plus x to the 1 plus x to the 2. So I'm saying something about now the possible solutions for y1, they become the powers of x. And I'm doing the same thing for the other things. So I'm getting x to the 1, x to the 2, plus x to the 3 for John, because he either wants 1, 2, or 3 apples. And finally for Aya, I'm getting x to the 1 or x to the 2. And I can solve that. I have to multiply everything with everything. So for example, I could multiply the first element of this with the first element of that and the first element of this. Then I'm getting x times 0 times x times, let's be slow. So here I'm getting x to the power 0, x to the power 1, and x to the power 1. And that is x to the power, I have to add up the powers, so x to the power 0 plus 1 is 2. Okay, then I have this one plus times this times this. Okay, next one would be, for example, this one times this. Might be x to the power 0 times x to the power 2 times x to the power 1. Or I'm choosing, so now I've chosen here the 0, here the 2, and here the 1. But I could also choose here the 1 and here the 2 and get the same coefficient. Or I'm choosing here the 1, here the 1, and here the 1, and in all cases I'm getting an x to the power 3. And if I'm adding all these up, then is this actually a 3? Yeah, 3 to the power x tells me in how many ways I can choose my x from this sum, my x from this sum, and my x from this sum, such that if I'm multiplying them together, I'm getting x to the power 3. And this is really nice, because then My coefficient in front of it tells me how many ways there are to choose an x here, an x there, and an x there, such that the powers of them add to 3. This does the job of counting for me. So for example, if this one is first one, Alice gets 1 apple, then I'm having an x to the power 1 here. Maybe. So a combination of apples here already used. So for example, the first apple, Alice could have 1 apple, John could have 1 apple, and Aya could have 1 apple. That means that I'm adding up and multiplying x to the 1 times x to the 1 times x to the 1 or x to the 3. That's a situation where there's 3 apples in total and each of them eats 1. So you see that powers of the axes keep track of a counting problem. And now I don't want to explain it much more, but I just want to show you what's the result of this procedure. So you just write down, you're multiplying everything with everything, and then you're just adding everything up. And you know how to do this algebraically. It's just, as I started expanding the sum, if you're lazy, then you can ask Wolfram Alpha to expand it for you. And if you do this, then at the end of the day, you're getting the following polynomial. X to the power 2 times 3 to the x3 times plus 5 to the x4. Let me just, so this is 2, 3, 4, 5, 6, 7, and the coefficients should be 1, 3, 5, 5, 3, 1. Okay, perfect. And you see my sequence here. If you're writing this as a sum over ak x to the power k, that means that my ak's, there's no power 0, there's no power 1, there's 1 power 2, 3 power 3, 5 power 4, 5 power 5, 3 power 6 and 1 power 7, and then only powers of 0. I have my sequence here of the AKs encoded by this function of this polynomial. And these AKs, they answer an interesting question. Because this is A3, and A3 tells me how many ways are there to choose y1 plus y2 plus y3 such that they give 3. So this is the same as that one. No, this power 3 is the same as here. And these are the choices for Alice, the choice for John, and the choice for Aya. So how many ways are there to choose integers out of these sets such that their sum is 3 corresponds to A3 in the sequence, or the coefficients of the power 3. So this, I'm doing it one time here as well, so that you're clear about what's the coefficient and what's the power. So this one is A4 is equal to 5. So A4 is the answer. How many ways Alice, Aya, John, and Aya can distribute four apples within the constraint. There are 5 ways to do this. So the answer is 5. Still on board, yes. Okay, so and so you could think of this f as being the product of the generating function of. So you have something like this. No, it's not on board. So let me write this. So you could write fs as the product of a G1 for Alice times a G2 for John times a G3 for Aya. So this one is my G3 of X. And that means that my generating functions, if you multiply them together, so this is of course the product, that gives me a generating function which combines the ways of doing something. So let's remove this and just talk a bit about the general picture here. So for Alice, she does want either 0 apples, or she wants 1 apple or 2 apples, and 0, 1, or 2, and not more. So her sequence is 1, 1, 1, and then followed by a number of zeros. So this is for Alice. And the generating function, well, then you take G1 of X is X to the 0 plus X to the 1 plus X to the 2. These are all coefficient 1s, and then 0 for the other ones. And John, likewise X to the 1 plus X to the 2 plus X to the 3. Or his sequence is a 0, a 1, a 1, a 1, and then many zeros. And then you do the same thing for Alice and John and Aya, and then you can write down the product of the generating functions. And the product of the generating functions is the product of polynomials. And if you multiply everything out and write it as a sum over the ak x to the ak, then the x and then the ak answer you an interesting question about how many ways are there to. I have asked this question before. Let me not write it. Let me just say how many ways to distribute k apples. Okay. I think here I can stop, and the rest I'm putting from the old lectures. Thanks for paying attention. So I'm not doing this completely alone. Have a nice evening.